Hey everyone. So in this video, we're going to be talking about this work energy principle we've mentioned already a little bit before, systems, which is a pretty easy, straightforward idea, non-conservation, which is where we don't always get the energy we put in back, or we can't always get it back, as well as power. And I don't mean over 9,000, but more like light bulbs and things like that. And before we write anything, I want to zoom in over here and kind of look at an example. And an example I have here is I have a block, and it's just some big block, who knows what it is. And here I am, or you are, any little kind of, I guess, bald stick person. And our block is going to be greater than 0 degrees Celsius. And so what that means is it's going to start melting the ice below it. And you can see I have a little layer of water essentially right here. And so we have this block that's on water, this little kind of slippery cushion, and it's like buttery smooth is what really happens. And it ends up kind of giving us a coefficient of friction that essentially is 0 between the block and the surface of the ice itself, which is kind of neat. And so what that means is every little bit of work that you do, which means that every bit of force that you apply over some distance, is not going into friction. It's not going into heating anything up. It's going into, well, this block that you're pushing. So maybe you have some spiky cleats on, but this block is going to move with like no loss of energy, essentially. We can ignore air resistance. And so if you think about it, well, where the heck is all this work you're doing going? Well, it's got to go into making this block move faster and faster and faster. And so in the beginning, maybe it starts at rest, so its initial velocity is 0. But over here, once it's kind of moved over to some other kind of portion of the ice or whatever, maybe it's going so fast that you can't even catch up to, and it's just gone, right? It's just sliding on this frictionless surface essentially forever until it crashes into something. And so what this idea and diagram is showing is this work energy principle. And it's the idea that the energy that you put into something went into changing its kinetic energy. It's going really, really fast now. All right. And so that's really all this work energy principle is it's saying that as you do network, so as you do overall work on an object, you change its kinetic energy. And that is this work energy principle. You lose energy, it goes into something that's going to make it move faster, typically is the case. And we'll bring in things like friction and things that kind of fight against us in a little bit. And so, kind of in a symbolic term, we'd say, well, wait, the work that you do is the change in kinetic energy, which is the difference between the final kinetic energy and the initial. This is just the kinetic energy equation twice. The little f below the v means final. The little I below this v means initial. That's it. That's all it is. And so in the case of my example here, we can talk about a system and the surroundings. In the example we just looked at here with me or you pushing a block on this ice, well, the system is just the stuff that you choose to focus on or analyze. We weren't really caring about, I don't know, some mountain way off in the distance or something. We didn't care about a car that's parked over off on the side over here. We didn't really care about any of these other things. We just were looking at the block on the ice and you pushing it. So the system is really whatever you are choosing to look at. All right. And that's it. It's as simple as that. It could be a cup, it could be a block, it could be something pushing against the spring, it could be the spring itself. But the system, you get to choose. And the surroundings is literally everything else. And in the extreme example, that really does mean the rest of the entire universe, which is kind of bizarre. Now, in the case of us, though, we typically aren't going to talk about how you doing something or picking up a cup is going to change the energy of some distant planet. But there really are exchanges going on between us and all of the universe around us. And so it's just kind of good to know that, oh, well, maybe the system is losing energy. Well, where's it going? It has to be going into the surroundings. Or maybe a system is gaining energy. Oh, well, if the system gained it, where could it have come from? Outside of the system, the surroundings. And we'll kind of start talking about things that way. Now, we've already mentioned this a little bit, but a non-conservative force, non-conservative, non being the key word, are just those or forces that don't follow conservation of energy. That means you cannot get the energy back. And an example I believe we've already said is you go and you warm your hands up. You're rubbing your hands together, right? you are totally using energy to rub your hands together, and there's some friction, and so your hands warm up. Well, you don't get that energy back. In the case of, I don't know, maybe you picking up a baseball or something, if you drop the baseball, well, you put energy into it, you did work to pick it up, it has potential energy, and if you let go, it's going to gain all that energy back as kinetic energy. But not all things are conservative forces. Gravity is a conservative force. Springs have conservative forces, but not all things are conservative. And so some of the big ones to know are friction, that's super non-conservative. Drag, that's kind of an air resistance, essentially. An air friction really is kind of the idea. There's drag on a car as it goes faster. If you go jump out of a plane and you're skydiving, there's drag on you. It's air resistance. So those are kind of two of the big main ones. Tension is also a non-conservative force. You can pull on a rope all you want, and you're not going to get that energy back out of it that you're kind of applying to it, unfortunately. And so let's look at kind of an example. How much work is done by non-conservative forces? That means out of like friction, drag, tension, those. How much work is done by these? Okay. On a moving 5,000 kilogram car, we have a period here for sig figs, and it travels 30 meters. Okay. So we know a mass, we know a distance, and we're given the fact that it's going at a constant velocity, and we're told the coefficient of kinetic friction. Okay. So I have my car here, and I've just labeled my four forces. You don't have to use different colors. I did just to kind of make things really clear cut. And we get that, well, gravity and the normal force, these are always kind of balancing each other out, right? They're kind of equal and opposite. And if it's going at a constant velocity, it's not accelerating, it's not slowing down, it's not speeding up. That should indicate to us that, hey, friction acting backwards is acting just as hard backwards as my push force is acting forwards. These two are also balanced out. They're equal but opposite. And if push was bigger, well, it would be speeding up. If friction was bigger, it would be slowing down. So we have this constant velocity. So I know now that my frictional force and push force are equal. So what the heck is this asking us to do? How much work is done by non-conservative forces? Well, friction is really our main non-conservative force here. How much work is friction doing? So if that's really the case, we'll need to use this work equation. We need to figure out, well, what is the force? Well, we need to find the force of friction in this case, and how far. Luckily, we know D, it's this 30 meters, so we can just plug that in. So really, all we have to do at this point is find friction and plug it into this. That's really it. That's all we have to figure out. So this is kind of a throwback question now, really. It's going, oh, well, what the heck is the force of friction? Well, we could look back and find in our kind of AP equation sheet that friction is mu times the normal force. But we already have said that the normal force is equal to gravity, and gravity is just m times g. So we know the mass. It's right here. This is 5,000. So I should be able to plug into this gravity equation here and substitute that for my normal force. So doing all of that now, kind of maybe slowing down a little bit, we can see that this friction equation becomes not mu times the normal force, but now mu times m and g. And so we know mu, we know m, we know g. We can just plug in all of this here, and we get that friction is this whopping 19,600 newtons. So what do we do with it? Well, that is our force. That's the force, that's this non-conservative force that we want to find how much work it's doing. So I can just plug in my two numbers here, and we have our force, we have our distance, and I get that, oh, this much work is done by non-conservative forces. This is how much energy goes into essentially friction, which is really just the heating of the road, it's the heating of the car tires, it's all of the friction, and this is all energy that I cannot get back, is really the idea for it. Now, our next kind of big idea is just this topic of power. And so what the heck is power? You go and you look at a light bulb in your house, you go, oh, it's 80 watts, it's 100 watts, it's, I don't know, 9,001 watts, right? Well, power is just the rate of change of work per time, or energy per time. So it's really easy. You just go, okay, well, what's the amount of energy? And what's the time? You go, oh, I used 1,000 joules over 10 seconds. Well, you would do 1,000 joules divided by 10 seconds. You go, oh, well, it's 100 watts is really the idea. So it's pretty straightforward, but you need to be comfortable finding energy first. And so that's why we did this example with work here, because this was finding the energy that was really used by these non-conservative forces. So the units for power are watts. Yeah, that is watt, I said. And really, a watt is just a joule per second. So if, let's say, it took the car above 25 seconds to go the 30 meters, I've just given you the time that we will plug in right here. So we know the time, we know the energy from up above. So what is the power due to non-conservative forces? Essentially, how powerful is friction is kind of what we're asking. Well, we know the energy, we know the time. I divide one by the other and we get, oh, friction is at a power or a wattage of 23,520 joules per second. Or we could write it as 2.35, and we can maybe just leave it at 2.4 if we were really following sig figs, times 10 to the 1, 2, 3, 4 watts. So that's the other way you could have written that. And so really, that's all it is for power. It's pretty straightforward. It's pretty easy. You just got to know this guy, and it is on our AP equation sheet. I would challenge you to go find it, actually. And I want to just do a little reminder of something. This is something you should have in our previous page of notes, so you don't necessarily need to write it. But I wanted to mention it because they use this term a lot on the AP exam. They talk about mechanical energy and what the heck that is. So mechanical energy is just the total, the sum, so the combination of both the potential and kinetic energy an object has. So I drew just like really quickly this little silly roller coaster example. And so if there was no non-conservative forces, so there's no friction, there's no air resistance, there's no drag, there's nothing weird that is going to like dissipate energy, essentially, like no sound even, because sound is dissipating energy. So if there were zero or no non-conservative forces, what that means is that the mechanical energy, this thing, is going to be constant forever over this entire kind of loop-de-loop track. And so really, we could look at a couple key points. We could say, well, if this is the max here and it like just barely stops at the top, well, you would say, oh, it's all potential energy due to gravity here. You go, oh, well, down here at the bottom, it's all kinetic energy. It's the same thing here. It's all kinetic. And here it would be both. It'd be gravitational potential and kinetic. And here it would also be both because it's not as high up as up here. We could go through and kind of label all of these, but I have to tell you, since there's no non-conservative forces, there's no drag or friction or air resistance, the total amount of energy is the same in every single one of these circumstances. The mechanical energy is the same, and the mechanical energy is just the total of both. And so it doesn't really matter how we look at it then, and kind of in terms of, oh, is it kinetic or is it potential? It's just saying the total sum of the energy that we can get back, which is this potential and kinetic, is constant, is really what it's saying here. In circumstances where there's no non-conservative forces, so you have like frictionless surfaces, really is kind of the idea. And just to reiterate, the roller coaster here is going to have the same amount of energy at all of these different points and everywhere along and in between on the track here, because that mechanical energy would be conserved. So you don't need to add this. Hopefully that just made sense. We really get a good, strong understanding of what the heck mechanical energy is, because we'll be using this more and more as we progress on our unit. So thanks for watching.